Okay, the photoelectric effect. The first person to notice this was Hertz, but the person who really gets the credit for it is Albert Einstein. In the same paper in 1905 that he published with special relativity, there was this observation, and they finally awarded him his Nobel Prize based on this. The photoelectric effect is proof that light is a particle. That's what it's all about. That light is, you cannot explain what he saw using wave theory. Now, we knew that light was a wave. Thomas Young, light reflects, refracts, diffracts, interferes. That's true. Light's a wave. Einstein comes along and proves conclusively that light's a particle. Photoelectric effect. Again, I highly recommend that you first look at page 343, chapter 18, the quantum world. All right, you need to know the photoelectric effect. They always ask questions on this on the AP test, whether it's multiple choice or a free response question. It's very important in physics. It's also chapter 27, starting on page 877 of the textbook. All right, starting on page 877 of the blue textbook. Okay, so take a look at that. It starts at the very bottom of that and continues on. Now, the photoelectric effect. This is the theory behind solar electricity. Well, some solar electricity. When you think of a solar cell and sunlight or whatever strikes it, and you can get an electric current out of that. That's this. So you have certain pieces of metal where this works, and others that don't. So let's take just a piece of metal, all right? There's this piece of metal, and sunlight strikes that, all right? So there's light coming down and hits this. This is called the emitter. Emitter. This picture is much better drawn on page 878, and it's also drawn in the green Mooney's book. Mooney's book. I'm selling that. I'm telling you, it's a good book. That's the emitter. Light hits it. If you're going to get a current, the light hits it, it kicks off electrons. And then those are going to be collected at the, wait for it, the collector. Okay, E for emitter. And then here's another thing right here, and that's the collector. This is a vacuum in between. All right, these things would be contained in some sort of container here. That's a vacuum in between. And then we come on over here. These are wires, all right, over there. And you have to have some sort of variable power source here, all right? Variable power source. So it looks like a battery with a little arrow through it. That means we can just change it. And then that's connected over here. We're going to put an ammeter into the circuit. We also want, just because we want to figure out what's going on here, we want to put a voltmeter across this, all right? So that voltmeter is going to read what's across the variable power source. It also reads what's across here, right? That's our basic setup. The thing that's curious, light strikes, depends on the type of light, all right? If you have some low frequency, it depends on the type of light, and it depends on the type of metal, right? If you have some low frequency light, you get nothing. And then as you increase the frequency, decrease the wavelength, then for certain types of metals, you start to record a current through here. So let's start off with the voltmeter at 0. So the battery's not helping at all. So the battery's not helping. You got no potential difference here. Just wires connected to these two plates. All right, and then you shine light on this thing, and as you decrease the frequency, light strikes it. The electrons in the metal start to absorb some energy from the light. They start absorbing some of the energy, and then when they get enough energy, remember they're starting to get more energetic, all right, because they're absorbing light energy. Whoa, we're getting warm, all right. And then eventually they get enough energy that it's more than the ionization energy of the metal. Remember, metals hold on to their electrons rather loosely. And so some of these things are going to start to leave, all right. Now, remember, there's no potential difference here because the battery's not on. So some of these things start to leave, and some of them have kinetic energy, and they start traveling over here, and then they connect over here, and we start to record a current in the circuit, all right? It's interesting, though, it doesn't always work. Some metals don't do this, at least some metals don't do it, and some frequencies of light don't do it. Okay, now, we decide, well, that's interesting. If we take this battery and we start to make it negative, remember, these are electrons. And they sometimes call them photoelectrons. But these are little electrons that are going over here. So what if we make that plate negative? So we set up a potential, we turn on the battery here, the power source, and we set it in such a way that this is reversed, and we have a negative charge here and a positive charge here. Well, these electrons are coming over here, and they're going to be repelled by that, come to a stop, and say, whoa, and they're going to repel and go back to that plate. But some of those, the ones that have the most energy, some of these electrons that have a lot of energy, might still make it over there. All right, and what we're really interested in is we're interested in those electrons that have the greatest kinetic energy, because the electrons are going to be kicked off and have different amounts of electricity as they absorb the light. Kinetic energy. So some of these things, they start going over there. You've got a negative plate here, and a lot of the electrons are going to just come on over and slow down because that's negative. We're being repelled. They're going to stop, turn around, and go back over there. But a few of them are going to have enough kinetic energy. They slow down, but boom, they still make it over there. All right? So you say, well, that's unsatisfactory. So you make this more negative. And you keep making it more and more negative until you reach the point where eventually even the most energetic electrons can no longer make it there. Now, that voltage that corresponds to stopping the most energetic electrons, the ones with maximum kinetic energy, that voltage that corresponds to stopping even the most energetic electrons is called the stopping voltage. And how do you know you've reached the stopping voltage? You crank this thing more and more negative until you no longer get any current. So at first you've got some current passing through because you're shining light, electrons are making it, you're recording a current in amps. And then you reverse this so that's negative, and so you're starting to repel electrons, and so the current starts to drop. And then you increase it some more, so that it becomes more negative, so fewer electrons make it, so the current goes down even more. Then you make it even more negative until eventually you reach that point where it stops. Again, that is called the stopping voltage. And we use a delta V subscript S to represent that. All right, let me just pause this.